Okay, I guess we can start. Hello, everyone. It's good to see so many people and in presence and also at home. And welcome to this tutorial on which will be an hands-on explainable recommender system with knowledge graph. As you can see, we are 4 presenters. 2 of us are here and one of us could not join and one is at home. I will start, I will leave the floor to the first presenter to introduce himself.
Hi everyone, I'm Giacomo Balloccu. I'm a PhD student at the University of Cagliari. I'm a Hugging-Face talent ambassador, and also I will join Amazon for an internship as a applied scientist. And I'm very glad to be here and to present this tutorial about my main research topic. So yeah, I hope you enjoy.
Hi, I'm Ludovico Boratto, and I'm an assistant professor at the University of Cagliari, also in Italy. As I said, Gianni Fenu unfortunately could not be here today, and we have the 4th presenter who is joining us from home.
And I'm Mirko Marras. I'm an assistant professor at
Mirko,
University
we can
of
hear
Cagliari.
you.
Can you hear me?
Just 1 second. Okay, try.
Can you hear me?
Yes, perfectly. Thank you.
Okay. And I'm Mirko Marras. I'm an assistant professor at University of Cagliari too. Welcome to this tutorial.
Okay. Okay, so we will start with the outline for this tutorial, which will be composed by 2 sessions. In the first one, we will start, and we are now in okay. The first in this first session, we are starting with these opening remarks, and then I will head straight to an introduction on explainable recommendation. Then Giacomo will introduce the first notebook, which will show us how to interact with the data sets that have been enriched with the knowledge graph. Then we will continue with some slides on explainable recommendation models, methods, sorry. And then we're going to have a 10 minutes break. Then in the second session, we will continue with an hands-on where we will present 2 of the state-of-the-art models that can introduce explainable recommendation with knowledge graph, which are GDPR and CAFE. Then we will continue with the evaluation of this type of methods, both from like a theoretical point of view and from a practical point of view with another hands-on. We will conclude this session with some challenges and some future directions. You can ask questions at the end of each session. Hopefully, we will be able to answer all of them. For those questions that are remaining, we will be available, of course, offline. So, by the end of this tutorial, you will be able to understand what are the principles behind explainable recommender system and what is the underlying data that allows to generate explainable recommendations. Then you will also be able, from a practical point of view, to load, format, and the parse interaction data that has been augmented with knowledge graphs. You will also know what are the main methods and the characteristics of the state-of-the-art approaches that perform explainable recommendation. And you will be able to build and train 2 of the state-of-the-art models, which, as I mentioned earlier, are GDPR and CAFE. Then you will know what are the core strategies for the evaluation of this type of approaches, and you will also be able to generate and evaluate explanations starting from reasoning paths that have been generated by these 2 models. Okay, so without further ado, I would start with the first session, which, as I said earlier, will begin with an introduction on explainable recommendation. So this is a recommender system conference, so I don't think I need to convince you why recommender systems are important and why do we need to do things properly. So I will head straight into why explainable recommendation is important and mainly what is the goal of explainable recommendation. An explainable recommender system can basically support both the users and those that design a system at understanding why certain recommendations have been produced. And we can see that there are several advantages for those 2 types of stakeholders. Indeed, from the side of the users, we can enable perspectives such as transparency, persuasiveness, effectiveness, trustworthiness, and user satisfaction. On the other side, of course, for those who are behind the system, we allow them to understand what's going on with the generated recommendation, allowing them to diagnose the system, to debug it, and to refine possibly the recommendation algorithm so that things can be improved. One might think, okay, cool, then with an explainable recommended system, I can do all these things at once. No, the curious thing is that even though all these perspectives can be enabled, we can see that according to the way in which we generate the explanation, and during this tutorial, hopefully you will learn many ways in which explanations can be generated, different perspectives can be offered to the users. And in this sense, I will now give a brief introduction to this 2005, so quite an old study, which studied what's the trade-off when we present explainable recommendation between the satisfaction and the promotion. What do the authors think? What do the authors mean when they talk about satisfaction and promotion? The promotion is when a promotion happens when an explainable recommended system allows the user to adopt a recommendation, while a user is satisfied when the users can make more accurate decisions. So in this study, basically 3 different explanation styles have been introduced. Here on the top, you can see the first 2. The first one is a keyword-based explanation, which showed basically books that contain keywords that are of interest for the users and that have received a lot of ratings and that are high. And the second one is an influence-based explanation where the users basically can see which books that they have previously evaluated have contributed to the choice of the recommended items. So these 2 classes of explanations can help the users make more accurate assessments, so they lead to a good satisfaction. While neighborhood-based explanations, in which basically in classic collaborative filtering way, I tell you, I recommended you this item because your friends also like this item, lead users to overestimate the relevance of an item. So promotion happens, users actually adopt these recommendations, but they're less satisfied than with a keyword-based and an influence-based explanation. So the take-home message in this first part is that according to the way in which you will do your explanations, you will enable your stakeholders to have a different visions of what is getting recommended to them. Indeed, when we talk about recommendations, there are 2 main types of explanations. The first one is the so-called self-explainable or intrinsic explanation. This type of explanation is generated by an interpretable model. So this means that the decision process is transparent, and these models can naturally provide explanations to the users. And we will see some examples of this type of explanations in the next slide. The second class of explanations is known as post-hoc or model agnostic. And in this case, the recommendation has been generated by a model, which is a black box, but and so we need to create another explanation model to generate the explanations after the decision has been made. So you might ask yourself, why do we need 2 types of explanation? There are different factors why we would need to have these 2 types of explanations. The first one is rooted in psychology. So basically, when we make decisions, sometimes we are sure of why we're making this decision, and we're also able to explain right away why we have made a certain decision, and the same of course for the recommended system. While in other cases, we first make a decision, and then once we need to explain why we made a certain decision, we activate some other mechanisms that allow us to explain why this choice was made. And in other cases, it might be the case that the recommender system behind the model, behind the recommendation is too complex. So we might need some post-hoc or some post-hoc explanation so that the model can be, the recommendations can be explained. So let me go quickly through some examples of both classes of explanation so that you have an idea of what we can do with both types of explanation. The first one is probably the most famous example and also the one that we will follow mostly in this tutorial of self-explainable explanation. So as you can see here in this example, the recommendations have been generated thanks to a knowledge graph, which is a user item bipartite graphs that allows to recommend items to the users based on their history. So in this case, in this case, you can see that user 2 got recommended Romeo and Juliet. So the movie Romeo and Juliet. So when we need to make an explanation, we can use the same knowledge graph and follow the same reasoning path to tell them, okay, you got recommended Romeo and Juliet because you watched Titanic, where Leonardo DiCaprio was starring, and Leonardo DiCaprio is also starring in a movie that I recommended to you. So as you can see, both the model and the explanation are rooted on a reasoning path over the knowledge graph. So in this second example, which is a Cagliari 2014 paper by Zhang and colleagues, the authors have used a feature-based approach to explainable recommendation. And so basically you can see that here on the right, you have a list of recommendations and the user can pass over with the mouse and see each recommendation. Since the explainable model is feature-based, this model can also use the same features to show a word cloud to explain to the user what are the features that led to this recommendation to them. Moving to model agnostic explanations, we can see this approach by Wang and colleagues, which was presented at ICDM in 2018, where basically the recommendation model is a black box, and we have two agents that have two different tasks. The first one has the goal of predicting which is the relevance of an item using what we see on the right as an environment. So an environment is prior knowledge that I've collected about the users, about the item, and so this agent first tries to predict the rating. Then we have another agent that tries to build quality explanations. So basically, these agents get rewards if the explanations that it generates are good. And so as you can see, we have no knowledge about how the recommendation model is made, and we have these agents that try to learn with attempts both to understand what is the relevance of an item and what can be a good explanation. In this case, also in this case, in this approach by Pick and Wang, the recommendation model, which is a matrix factorization model, is a black box. And what did the authors do? Basically, they took, on the one hand, the user profile, so what the user has observed and has interacted with. And on the other hand, the recommendations that have been generated by this matrix factorization model. And what they did was to create association rules to create associations of the type, if you watch this, then you might be interested in this. And using these association rules, they can provide post-hoc explanations. Finally, as a final example, this RecSys 2018 paper that moved from pure exploitation. Basically, as you can see from the figure on the left, the authors question the fact that when there is a low certainty about the items, some models sometimes exploit these items for explanations and sometimes not. And what was done in this paper was to introduce a bandit method that instead of exploiting sometimes, they also did an exploration. So they tried to understand when the users interacted with certain items that are associated with an explanation. And so basically they combined exploitation and exploration and understood that both aspects are relevant to produce both more effective recommendations and better quality explanations. So how did we get very quickly to explainable recommended systems? As you know, the most simple type of collaborative filtering, which is user-based and item-based collaborative filtering, is able to tell you, I'm recommending you this item because you have watched something similar to this. And these ideas root from the late 90s. And as highlighted in this paper by Navatin Tarev and Judith Mastov in 2007, in the industry before Shai and all the technologies that we have now, in the industry, they were adopting already some semi-automatic explanation. What happened is that in 2009, basically there was this disruptive change in our community where collaborative filtering models changed thanks to the introduction of latent factor models and of matrix factorization. But as probably most of you know, these models are not the most explainable ones. So our community, from the sense of explainability, was a bit stuck for a few years. And as you can see in 2012, there have been advances, but from the content-based perspective. Then in 2014, the term explainable recommendation popped out thanks to a model that was introducing an explicit factor model. And then a lot of models have been introduced after this, and Mirko, during one of the next session, will introduce you to some state-of-the-art models in this sense. So I said before that we can generate explanations of different types. Let's try now to delve into what are the sources of information that we can use to generate explanations. As I said before, already from the late 90s, we are familiar. We got familiar with classic user-based and item-based collaborative filtering. So basically, we can generate explanations of the type, you got recommended these items because your neighbors gave good ratings to it. And already in the year 2000, there is this work by Locker and colleagues where they basically showed visually why an item got recommended. So basically, you can see that the majority of the neighbors of these users gave high scores to this item. Then another type of source of information that we can use for explanation are the features that characterize the items. And as you can imagine, this is mostly characterizing content-based approaches. And here as an example, we have provided you this work that was presented at WWW 2019, where basically the authors depicted the features that characterize the domain of the recommendation. On the left, it's hotels, and on the right, it's music. And basically, you can see here the user, which is depicted in red, and then the recommended items are in blue and green. As you can see, in both cases, the blue item is very close in terms of features to what the user likes, and this is why it got recommended. So basically, they use this radar chart to show the user why an item got recommended from a feature-based perspective. Then another very famous type of explanation is a sentence-based explanation, which can be generated thanks to two main classes of approaches. The first one is based on templates, and the second one is based on natural language generation. So as an example of template-based explanation or template-based approach, here there is the CIR 2014 approach, where you have templates that show you both from a positive perspective and from a negative perspective, why an item got recommended to you. So you might be interested in this feature on which this product performs well. So we have a fixed template, and based on the outcome of our recommendation, we can plug the feature that basically characterized our recommendation. From a generation-based approach, you can see here two very famous approaches. So as I said before, they use natural language generation and use information about the model to generate a sentence, or in some cases, a paragraph that explains why a certain item was recommended to the user. Of course, there are not just features and interaction data, but in most platforms such as Amazon, we have the possibility to provide comments and reviews. And these reviews are usually used to provide so-called opinion-based explanations. These opinion-based explanations can enrich both feature-based and sentence-level explanations by providing additional information. For example, if you look at the comment here on the right, two aspects that emerged is that the lens that in the end got recommended to the user is both great and it deserves the price that it costs. So this information that is based on the reviews is added as an extra form of explanation to the users. Finally, thanks to the recent advances of image processing, we are seeing a lot of advances from the perspective of visual explanations. So basically, our explanations can be visual and use characteristics of the image to explain the recommendations. Here you can see two examples, and on the left, you can see the item that got recommended, and in this approach by Lin and colleagues, the pixels that led to the recommendations are highlighted to the user. Or in the approach in the right, you can see that it connects the reviews with the parts of the item that are associated with the review. So if the review was talking about the neck, these approaches can clearly identify the neck and connect the review with the item that got recommended, so that the user can understand better why the item got recommended to them. Finally, social explanations exploit the power of our social interactions to provide better and explainable recommendations. So as you can see in this example from Pick and Wang, you can see that here in the middle we have a list of recommendations, and on the left you have a list of social users. What this approach does is to exploit this social interaction to tell the user why this item got recommended. So for example, there is a high similarity with, I don't know, user U3, who is not a friend, and then the system allows them to understand why the item got recommended, also exploiting the social perspective. For example, why U5 is similar to you, because you like items D, E, and G, and you don't like item H and I, and so on. Okay, now let me move to another perspective, which is also important about explainable recommendations, is that when we introduce explainability, we are inevitably affecting or interacting with other properties of a recommender system. And in this section, I will give you a bit of an overview of what are the dimensions of a recommender systems can be impacted by explanations. The first one is clearly the utility, the effectiveness of the recommendations. And here you have our recent CGIAR 2022 paper, in which we basically tried to introduce explanation path quality. And in one of our research questions, we asked ourselves, okay, what if we try to improve our explanation path quality? What is the impact on the NDCG of the recommendations? So in this paper, we considered three perspectives, which are the recency of the linked interaction, the popularity of the shared entity, and the diversity of the path type. And you can see that these three perspectives impact very differently on the recommendations quality. Indeed, in terms of recency, sometimes when you introduce recency, the recommendation quality improves, and in other cases, it decreases. So there is a trade-off that you always have to consider when introducing explanations. Moving to ethics and law, I will not delve too much into this aspect because exactly 2 months ago, there has been a fantastic tutorial at Cagliari 2022, which I invite you all to see, and you see it linked here, both in terms of reference and of link, where Marcus shared Elizabeth Gomez and Elizabeth Lex basically provided a very rich overview of how explainability in recommender system is impacted by ethics and law. So you can see here that both in Europe, here in the US, and in China, there have been several regulations that have been put forward in order to make sure that the recommender systems are more and more explainable and understandable by the users. Diversity and business are two other perspectives that are impacted by explainability. And here as an example, I've chosen this Salesforce paper, which was presented last year as an applied paper at CIKM, where basically the authors have shown that at Salesforce, they have these explainable models, but sometimes it's important to them to introduce diversity. Why diversity? To make sure that the developers of new apps can get enough exposure in their platform. So what they did, as you can see here, I put a screenshot of the loss function where you have the prediction produced by the model, but you have a component that accounts for the diversity. So they measure the KL divergence between the diversity that is currently ensured by the system and the desired one. And the explainability part of the model is a feature-based explanation, which I mentioned earlier, which accounts for the important features or the relevant installed apps by the users. Novelty is another perspective that can be impacted by explainability, and you can see this in this paper where they basically try to combine to generate explainable and novel recommendations. So as you can see here, they modified the matrix factorization algorithms to account both for explainability and novelty. And here from the screenshot of the results, you can see that when you maximize explainability alone, you can also maximize the NDCG. As soon as you try to combine explainability and novelty, the quality of the recommendation decreases a bit. So again, there is an interplay between these two properties, and you have to be careful about what you choose and what is the impact for your system. Finally, an interesting perspective, which is not very algorithmic, but we believe that it's very interesting, is that of trust. Clearly, as you know, as I mentioned also earlier, explainability can help users achieving trust. Let's try to see why. Basically, our algorithms are so complex that it's natural that initially the users do not trust our systems completely. So basically, trust can be used during the experience of the users with the recommender system as a means to enable trust in the system. So here you can see these two screenshots from Google Book, which is very interesting, where you can explain the users what's going on with your model so that the users can generate trust. For example, here we have a path recommendation during the night, and the explanation says, be careful, it's after 6 p.m. and our route recommendations do not include lights. Or on the right side, you can try to use explanations to try to show to the users that you're confident about the recommendations that you're doing to them, and again, enable trust. So in this case, in this urban path, we are showing them that we are 93% confident that this path suits the interests of the users. Finally, and very quickly, as I said, to generate explanations that are we need additional sources of data in terms of features, in terms of knowledge graphs, and here there is an overview of how the data sets that we all use can be enriched with additional information. You can see that there are different domains, movies, books, and news, and of course, the sources of information can be various in order to enrich these data sets. And here in the second slide, you have also product data sets, point of interest data set, music data sets, and social platforms. Here in this survey that is very recent, you will find many more details about this. So now I will leave the floor to Giacomo, which will introduce you to our first hands-on.
Hi again, everyone. So you can scannerize the QR code to join our collab notebook. There will be all the instruction to follow our tutorial if you want to run the cells with us. And the tutorial is a self-paced tutorial. So if you want, you can take it at home and do it by yourself. All the information are there. So I will leave you some seconds to scan the code, and then we can start. Okay, so let's start. Okay. Yes. No, it doesn't need it because all the pre-trained, we have all the pre-trained, so we don't need that. We will just show how to compute the models, but we will not do that. So let me increase the size of the notebook so it's readable for everyone. Okay. So as first step, we have insert a guide to get started. So what you need to do is to enter inside our Google Drive folder, which is the first link that you see in the Get Started section, and that you need to go on the RecSys 2022 tutorial on your drive, and from there you need to press on it and select a shortcut to your drive. In this way, you will have the tutorial and all the folders in your drive, and you will be able to run this code using all the files that we have. So yes, these are all the steps. Then you just need to mount your drive. I will do that as well. And we are ready to start. Okay, so in this part, we'll focus on loading and preprocessing our data sets. In particular, we are covering three different data sets, which are based on different domains. And these data sets are one based on the movies, which is MovieLens 1M. For music, we have Last.fm. We have in particular Last.fm 1 million, which is a subset extracted from the 1 billion dataset, which is a very huge dataset, so we need to reduce in some way. And from the e-commerce dataset, we have the Amazon cell phone dataset, which is extracted from a huge collection of datasets from the Amazon e-commerce. So in this notebook, we will load them. We will load the knowledge graph, which are extracted from different knowledge base, and we will perform the preprocessing, and we will save the datasets in a standard format that will be used later to perform mappings and to run the GDPR and coffee model. Here you can see an outline. We will cover mostly the ML1M part because the part of Last.fm and cell phone is pretty similar. Okay. So as first, we will import our packages, and we will work mostly with pandas. So if you are not familiar, don't worry, because we will cover most of the code that we will use in this tutorial. So it could be useful also to learn something new. So here you can see the structure of the data sets, and you can see that the structure is very different because they have different file names, different formats, and also this makes it difficult to to run and to execute our models. So what we're going to do is to transform all these datasets in a standardized format that will carry all the information that we need. So as you can see, here is the standard format. So we will have 3 files, user.txt, products.txt, and ratings, and these will be their structures. For the knowledge graphs, instead, I will give you some knowledge here. And a knowledge graph is pretty much a graph which is composed by nodes, which are entities in the real world, and relations which are relation that exist between entities in the real world. The knowledge graph for recommendation usually is composed by a set of triplets. For example, here A and C, where A is the entity head, B is the relation that connect with the entity tail, which is the C one. For example, this can be a particular movie is starred by an actor. So in order to use the knowledge graph, what is done for the recommendation is to link the offline dataset to a knowledge graph, which is usually stored in a knowledge base that can be Wikipedia, DBpedia, or Freebase. And what is obtained is a linkage which is composed by the ID of the dataset offline and the ID of the entity, the same entity in the knowledge base. The knowledge graphs are also, for recommendation, are also composed by 4 files. So the first is the linkage that we say now. Then we have the set of entities, which is composed by the unique entities of the dataset. You can imagine that might exist different entity types. For example, in the movie domain, we might have categories, actors, directors, cinematographers, etc. Then we have the relations that connect the movies with the external entities, which might be starring, belong to, etc. And then the set of triple, which is composed by all these entity head relation and entity tail triplets. Again, we will convert the knowledge graph in a standardized format, which is composed by these 4 files, which correspond with this structure. So let's start with moviness. So here you can see the internal structure of the moviness dataset, and we will load, visualize, and preprocessing before saving in a standardized format. As you can see here, I'm loading I'm setting as a path the moviness path, which is in the data folder, and I'm reading using the pandas data frame, the users files. As you can see, it's composed by user ID, gender, age, occupation, and zip code. And we have 6,040 users. Then we will load the movie file, and again, we can see how it's structured, and it's composed by 3,083 movies. Then we can load the ratings, and this takes some time because they are 1 million, but should be short. Okay, so this is the overview of the dataset. Now we will move on the knowledge graph, and here is the structure, the specific structure of the DBpedia knowledge graph, and we will load the files. So again, this is the entity file. As you can see, entity ID represents the entity in the knowledge graph. So an ID between 0 and the number of entities. And the entity URL means the link that connects to that particular entity. You can also use the link to see the entity on your browser and see what are the connections that exist between these entities and other entities. Then we have the movie to KGDF, which maps it's pretty much the linkage that we said before, which maps the offline ID with the entity URL and so the entity of the knowledge graph. As you can see here, we have 3,300 movies, which is less than the one that we had before. So we need to do some preprocessing about that. Then we can load the triplets. Here are the triplets. So entity head is an entity which should be a movie. Entity that should be an external entity, and the relation it's a number that tells what are the relations that exist between these two entities. This is the relationship file. As you can see, the ID is associated with a URL in the knowledge base. And we have different relations that can exist. So let's start with the preprocessing. So one of the first problems when dealing with knowledge graph is the fact that the knowledge graph, the linkage maybe doesn't contain all the items that we have in the offline dataset. So what we need to do is to discard the items that are not linked. And here you can see that the original dataset has more movies compared to the KG that we have. So we will use pandas, and in particular the easing function plus the slicing to remove the items. And as you can see, we have removed 582 movies. Then we will perform a merge to see if we have other items that are not mapped. And as you can see, we have lost also 40 items, something like that. Okay. Okay, yes, you can see that we lost 45 items. Okay, since we have done this removal, we need to propagate that on the ratings file, and we will do that with the following slide. So we are removing the relations, the ratings that involve a product which is not which is not anymore in our knowledge graph. Okay, so the other preprocessing is to reduce the dataset to its K-core, which is also called the threshold discarding. And this means that we will reduce the dataset to a dense subset. And to do that, we will do a discarding of the users and the items based on this K value. So with that, we will reduce the dimension of our dataset, and will be easier to make our computations. And this is usually done also in papers. So for the reproducibility perspective, you need to pay attention when someone does that, because they can obtain results which are slightly better because they are removing items which are very unpopular, or for example, which are not very present in the interactions. To do that, we use the masking, and we do that using pandas. And with this masking, what we are doing is firstly to count the number of occurrences of the users, the number of occurrences in the movies or in the ratings, and then using the mask to discard the movies and the users that have more than 5. Less than 5. Okay, yes, as you can see, this map will return true if they have more than 5, and with that, we can apply the mask and remove the items. As you can see, we have removed 4,000 ratings. Okay, since we have done this removal, we need to propagate that, of course, in the users and the items files. And as you can see, our threshold removal, I haven't removed any items, so we don't need to do anything in this case. Let's see regarding the movies, and we can see that we have removed some of the items. So since we have removed some items, an important thing to know is that when we reprocess our dataset, we need also to pay attention about our knowledge graph. We need to have them always updated to the same version, because otherwise we will have a lot of problems with the mappings. So we will use our function, which is inside the knowledge graph utils module, and we will propagate the item removal to the KG in this way. And as you can see, this code will produce the number of items that have been removed from the files. Okay, after that, we can save our preprocessed dataset in the standard format. This is the standard format that we decided at the start, and we will enter the preprocessed folder to save the file there. So for the user file, the first thing that we do is to drop the attributes that we are not going to use. In this case, the gender, the age, occupation, and zip code. So we will leave only the user ID, pretty much, of the users. Then we will add a new increment ID, and between 0 and the number of users, and we can save this new file into the user.txt in the folder where the dataset, where the preprocessed dataset will be. Also, we save this mapping between the old ID and the new ID in a dictionary. We can do the same process for the movies. So we will drop the attributes that we don't need, like movie name and gender, and we will add the incremental ID. and we save a mapping between the old ID and new ID. Then for the routings, what we'll do is to use these mappings that we have created between the old ID and new ID to propagate that in the ratings. So we will use the map function that what it does is to convert the elements that have value as the key of the user ID to new ID with the value. So here you can see that the ratings are updated. Then we can save our ratings in our preprocess folder. Then after this, we will move to the preprocessing of the knowledge graph. And the first problem that we need to deal with is the cleaning wrong formatted triplets. So in particular, we are interested in triplets that start with a movie and end with an external entity. So they might exist due to the collection or something like that. Yes, problem with the collections that we might have entities which are reversed or entity which are, for example, product-to-product triplets or entity-to-entity triplets. So we want to describe those triplets. And to do that, firstly, we will see the movies that are correctly mapped. And then what we are going to do is to create a mask that will check if in the triplets data frame, if the entity tail is in the movies. In that case, then the entity head should be a movie, shouldn't be a movie. And in this way, we will swap then the triplets which are in reverse order. And this code will do exactly that. So we'll swap the entities that start with that have an entity head which is not a movie and an entity tail which is a movie. Then we might have, as I said before, triplets which are composed by product-to-product, or entity-to-entity. And we need to get rid of them because we don't need that for our recommendation. Okay, so as you can see, this process has removed this number of triplets. Also, we need to check when we do this if we have removed some relations. In particular, we can check that counting the number of relations that exist now in our KG file, which contains these triplets. As you can see, we have 20, which is the same number of the initial one. So we don't need to do anything more in this case. Another preprocessing is the selection of the relations. And in particular, we can do something similar to the threshold discarding with the knowledge graph. So we can remove relations which is very sparse and not useful. And also we need to remove relations which doesn't make sense. For example, if we need to do, if we are going to do explainability for movie recommendation, we don't want explanations as explanation something like Inception is a movie because it is irrelevant or useless for our task. So as first, using this function, we will remove the relations that appear less than 300 times, but of course this number can be personalized based on how much you want the knowledge graph to be dense. And as you can see here, we have removed 7 different relations, and we need to update that. Here, you can see which are the relations that have been removed, making a comparison between the old one, which is this with 90, and this one with 30. Okay, so here among the relations, as I said, there are relations that are useless. For example, the 13, which is hypernym, and the other one is the 8. Which point, as I said, to the RDF type, which is in the case of a movie, it's film, so it's not useful because it tells us Inception is a film, and we don't need that. So we will drop these relations and all the triplets related to that. And this is a process which is very annoying to do, let's say, because you need to manually enter inside the relation URL and understand if this makes sense for the recommendation purpose, because it's very difficult to tell without checking the DBpedia page. So we have removed some relations, and we need to propagate that, of course, in the entities. So we remove some entities as well. And finally, we save the preprocess KG in our standard format that we saved before. So we will enter the preprocess folder. We will save our relation as it is, so relation ID and relational URL. Then the entity file, and we will do that as well without doing anything, any preprocessing, just to put the to CSV. The E2KG, and finally the KG with all the triplets. And we are done with this part. So the same thing can be done with Last.fm. You find all of the information here, and all the steps that we have done for this tutorial. Also, it's interesting to say, even though we will not cover this now in the interest of time, that the Amazon cell phone and all the Amazon datasets are composed using the metadata as the metadata to compose the KG. So they are not extracted from a knowledge base, but they are created ad hoc from the metadata. And you can see all the process here and how we will save it to the standardized format. But you will have all the already preprocessed dataset in the folder, so you don't need to do that now. So I'm done for this part. So I will leave the floor to the next speaker, which is Mirko. Mirko, are you there?
Thanks, Giacomo. Can you hear me?
Yes.
Okay, I see that there are a few errors and questions that
yeah, we'll try to solve them.
They're being mentioned in the chat. You can try to go over them during my talk and then in the break.
Yes, yes, of course. Okay.
Such that we are ready for the next hands-on.
Yes.
Okay, great. Let me share my screen. You can stop sharing. Oh, you stop. No, you can stop, Giacomo.
Oh, sorry.
Okay. Can you see the slides? Can you see the slides? Okay, great.
Yes.
So I can start. Okay, so thanks, Giacomo. And Giacomo gave us a practical overview of how to load and parse and preprocess both interaction datasets and knowledge graphs. And in the next minutes, we provide a short survey on explainable recommendation methods that use this data for providing recommendations, but also explanations to users. And we will focus on this kind of methods specifically applied on knowledge graphs. So recent research on model-based explanation recommendation is closely related to machine learning for recommender systems, as you know. One of the main classical ML models for recommendation is latent factor model based on matrix factorization. Matrix factorization methods are also commonly referred to as point-wise predictions methods, and they're also frequently used to predict user explicit feedbacks. Then we have pairwise learning to rank, that is frequently used to learn the correct item rankings based on implicit feedback. An example of this category is the well-known Bayesian personalized ranking, BPR. And then we have other models that adopt a list-wise learning to rank for collaborative filtering. And recently, deep learning and representation learning have also gained much attention in recommendation research. And these models, let's say that will work well when there is sufficient data for training, such as side information or knowledge graphs. And in our tutorial, we focus on this latter class of systems that are based on knowledge graphs. So this is just to give as also Giacomo and Ludovico already mentioned somehow, knowledge graphs contain rich information about the user and the items, which can help to generate intuitive and more tailored explanations for the recommended items. A KG is an heterogeneous graph where nodes denote entities and edges represent relations between entities. Items and their attributes can be mapped into the KG to understand the mutual relations between items. And moreover, users and user-side information can also be integrated into the KG, which makes relations between users and items, as well as the user preference, capturable more accurately. In this figure, you see an example of KG-based recommendation, where the movie Avatar and Blue Diamond are recommended to Bob. This KG contains users, movies, actors, directors, and genres as entities, while interaction, belonging, acting, directing, and friendships are relations between entities. With the KG, movies and users are connected with different latent relations, which can help to improve the precision of recommendation. But another benefit of this KG-based recommendation system is the explainability of the recommendation results. In the same example, reasons for recommending these 2 movies to Bob can be known by following the relation sequences in the user item graph. For instance, one reason for recommending Avatar is that Avatar has the same genre as Interstellar, which was watched by Bob before. Now we survey papers related to recommender systems that leverage these knowledge graphs to generate recommendations and accompanying explanations. Based on how these works utilize the KG information, we group them into 3 categories, also based on the survey that you see at the bottom of this slide. We have embedding-based methods, which can further be divided into 2-stage learning, joint learning, and multitask learning methods. We have connection-based methods that include methods based on metastructures and path embeddings. And finally, propagation-based methods, which can be based on the refinement of the user information only, the item information only, or of both. We now delve into each category with a short introductory part and a description of the core ideas of methods belonging to each category. Of course, we cannot cover all the possible methods for all the categories. We just provide you with a few examples and then further pointers for you to be read after the tutorial. And let's start with embedding-based methods. Embedding-based methods leverage fruitful facts in the KG to enrich the representation of items or users. There are 2 basic modules in this work. So one is the graph embedding module to learn representations of entities and relations in the KG. And the other one is the recommendation module, which is used to estimate user preferences for items with learned feature and then generate the top-end recommendation for that user. Based on how these 2 modules are associated in the framework, we categorize embedding-based methods into 2-stage learning methods, joint learning methods, and the multitask learning methods. Building a knowledge graph-based model in this category raised 2 main questions mostly. How can we obtain entity embedding with the proper knowledge graph embedding method? And how can we integrate the learned entity embedding in the recommendation module? We will see how prior work dealt with these two issues. Let's explore in more details 2-stage learning methods. The 2-stage learning methods stands for learning the graph embedding module and the recommendation module one by one. So in the first step, representations of entities and relations are learned with knowledge graph embedding algorithms. And then the pre-trained graph-related embeddings are fed into the recommendation module, along with other features from users and items to make predictions. In this category, for instance, Guan et al. Proposed DKN for news recommendation. As you can see in this slide, DKN takes 1 piece of candidate news and 1 piece of a user-clicked news as input. And for each piece of news, a specifically designed KCNN is used to process its title and generate an embedding vector. This model includes pre-trained word embedding specifically. By KCNN, we obtain a set of embedding vectors for a user click listed. And to get the final embedding of the user with respect to the current candidate news, they used an attention-based method to automatically match the candidate news to each piece of his clicked news and aggregate the user historical interests with different weights. The candidate news embedding and the user embedding are then concatenated and fed into a deep neural network to calculate the predicted probability that the user will click the candidate news. Wang et al. With another example leveraged KG for recommendation with better explainability in a sequential recommendation setting. The authors bridged recurrent neural networks with k-value memory networks for sequential recommendation. The RN component is used to capture the user sequential preference on items, while the memory network component is enhanced with knowledge of items to capture the user's attribute-based preferences. Finally, the sequential preferences together with attribute level preferences are combined in the final representation of user preferences. And to explain the recommendations, the model detects those attributes that are taking effect when predicting the recommended item. For instance, for a particular music recommendation, as an example, it can detect whether the album attribute is more important than others, where the attribute comes from an external knowledge graph. Yang et al., with another example, introduced a GAN-based recommendation model, KT-GAN, with external knowledge learned from item KG. This framework consists of two phases. In the first phase, various embeddings are distilled from different sources in order to fully represent users and movies. At first, they get a user entity embedding, denoted as EE, through a KG embedding algorithm. So as long as the movie is mapped into a KG entity. Meanwhile, the neighbor nodes of a movie entity in a KG are generally the movie attributes, like directors, actors, and genres. And they are used to depict the movie context embedding. That is the weighted sum of the attributes embeddings. Then they generate EE and CE as a movie's knowledge embedding, namely KE in the figure. And in addition, a user movie tag embedding, denoted as TE, is the average of all the tag vectors related to that item. When a movie key and T, when the movie embeddings key and T are both generated, they are concatenated, and they act as the movie representation. On the other end, a user knowledge embedding is the average knowledge embedding of the movies, which are the user favorite movies from the user movie interactions. At last, a user representation is the concatenation of the tag embeddings and the knowledge embeddings. And finally, in a second phase, a generator G and a discriminator D are constructed to learn optimal representations of the users found from the training set and the candidate movies representations generated in the first phase. In their framework, the advantage is that the representations fed into G and D are more indicative than randomly initialized vectors. So in this case, the vectors that we developed in the first phase are used as initializers for the vectors during the that we have that are used by G and D. And the final score Y generated by G indicates the extent to which a candidate movie would be preferred by a given user. Beam is another two-stage learning method we invite you to explore, but we will skip it due to the time. We'll see here the reference. The two-stage learning methods are easy to implement, since the KG embeddings are generally treated as extra features for the following recommendation module. And another benefit is that the KG embeddings can be learned without the interaction data. And therefore, large-scale interaction datasets will not increase the computational complexity. Moreover, the KG is usually stable, and so it is unnecessary to update embeddings frequently once they are learned. However, the entity embedding optimized by knowledge graph embedding models is more suitable for in-graph applications like KG completion. And since the KG module and the recommendation module are loosely coupled, the learn embeddings may not be suitable for recommendation tasks because they are not optimized jointly. That is what we see here for the next category, where we consider joint learning strategies for creating embedding-based recommendation methods. In particular, another trend is to jointly learn the graph embedding module and the recommendation module in an end-to-end training fashion. And in this way, the recommendation module can guide the feature learning process in the graph embedding module. As an example in this class, Zhang et al. Proposed CKE, which unifies various types of side information in a collaborative filtering framework, including items attribute level features, textual features, and visual features. Their model consists of two steps: a knowledge-based embedding and then a collaborative joint learning. In the knowledge-based embedding step, they extract 3 embedding vectors for an item entity from structural knowledge, textual knowledge, and visual knowledge, respectively. And then these embedding vectors indicate, let's say, that represent the item latent representation together. In the collaborative joint learning step, the final item latent vector would represent an item knowledge from structural content again, textual content, visual content, as well as historical user item interaction. And finally, these vectors are used for a collaborative filtering strategy by optimizing the pairwise ranking between items to learn about user latent vectors and item latent vectors. And the final recommendations are generated from these user latent vectors and item latent vectors as usual, as what we usually do in collaborative filtering. Another example, One et al. Proposed Shine, which formulates the user recommendation task as a sentiment link prediction task between entities in the knowledge graph. In general, the whole framework consists of 3 major components. For each tweet mentioned in a specific celebrity, they first calculate the associated sentiment and represent the user and the celebrity in this sentiment link by using their neighborhood information from 3 constructed networks. Then they design 3 distinct autoencoders to extract short and dense embeddings from these original sparse neighborhood-based representations, and aggregate these 3 kinds of embeddings into final heterogeneous embeddings. The predicted sentiment can thus be calculated by applying specific similarity measurement functions. And the whole recommendation model can be trained based on the predicted sentiment and the target sentiment. It is the ground truth obtained in the sentiment extraction step. Other embedding-based methods that similarly leverage joint learning are the ones you see in this slide. And again, we invite you to delve into them after this tutorial for completeness. The joint learning method can be trained end-to-end, and it can use the KG structure to regularize the recommender system as advantage. Nevertheless, the combination of different objective functions needs to be fine-tuned, which is often hard and time-consuming. And these are the 2 main disadvantages of this kind of a solution. To conclude with the embedding-based methods, we move to multitask learning strategies. In this class of systems, the recommendation task is performed with the guidance of the KG-related task. The motivation is that items in the user-item interaction bipartite graph and their associated entities in the KG are likely to share similar structures. Therefore, the transferring of low-level features between items and entities might be helpful for facilitating the improvement of the recommender system. In this category, again, One et al. Proposed MKR, which consists of a recommendation module and a KG module. The recommendation module on the left takes a user and an item as input and uses a multi-layer perceptron and cross-compress units to extract short and dense features from the user and the item, respectively. And the extracted features are then fed into another MLP together to output the predicted probability. Similar to the left part, the KG module in the right also uses multiple layers to extract features from the head and the relations of a knowledge graph triple, and outputs the representation of the predicted tail under the supervision of a score function f and the real tail. So the goal here is that given all the triples that describe our knowledge graph, given the head entity and the relations, to predict the tail entity. The recommendation module and the KG module are bridged by the specially designed cross and compress units. And this proposed unit can automatically learn high-order feature interactions of items in recommender systems and entities in the knowledge graph. Another example is that the solution proposed by Cao et al., KeyToop, to jointly learn the task of recommendation and knowledge graph completion. Intuitively, the auxiliary knowledge that we see here in the knowledge graph supplements the connectivity among items and is used as a constraint to model the user item pairs. And on the other hand, the understanding of user preferences to items should reveal their commonality related to some relation types and entities, which may be missing in the given KG. So on the left side, we have the inputs, the user item interactions, the knowledge graph, and the alignments between items and entities. The top right corner is tab for item recommendation. where we aim to optimize user and item embeddings for predicting the interaction vector. And at the bottom, we aim to predict the tail entity of a KG based on the head entity and the relationships. So this is the common KGE module. And KTAP jointly learns the two tasks by enhancing the embeddings of items and preferences with that of entities and relations in the knowledge graph. For this category, by applying the multitask learning strategy, it is helpful. Let's say, prevent the recommendation system from overfitting, and we improve the generalization ability of the model. Sorry. However, similar to the joint learning method, this solution requires effort to integrate different tasks under one framework. So we covered the major representatives from the embedding-based category. And to recap, we summarize here the advantages and shortcomings of each type of the embedding-based methods. So the two-stage learning methods is easy to implement. The learn entity embedding may not be suitable for the recommendation task. To solve this issue, initial entity embeddings are refined by, for instance, the GAN model proposed in Kitty GAN, or the Bayesian, the generative model that is proposed in DIN. And the joint learning method learns optimized entity embeddings through end-to-end training. And the multitask learning method further improves the generalization of the model by transferring knowledge from KG-related tasks. However, it requires plenty of experiments to find the optimal combination of different objective functions. Okay, so let's now move to connection-based methods. Connection-based methods utilize the connection patterns in the graph to guide the recommendation. Most works in this group utilize the user item KG to mine the relationships among entities in the graph. And the two main design choices for systems in this class include how to design proper metapaths representing the KG for different tasks, and how to model the connection patterns between entities in the KG. We will see now a few solutions to these two problems. And for this, there are two main approaches for exploring the connected information in the KG. We start with the first type of approach, which uses the metastructure in the graph, including metapaths and metagraphs, to calculate the similarity between entities. The metastructure-based similarity can serve as a constraint for the representations of users and items, or can be used to predict users' interests from similar users or similar items in the interaction history. As an example, Xi et al. Were the first to propose weighted heterogeneous interaction networks and weighted metapaths to consider attribute values on links in information networks. They designed a novel SEMREC method, which not only effectively integrates all kinds of information that are contained in recommender systems, but also flexibly represents different kinds of recommendation models through properly setting metapaths. In addition, SEMREC can obtain the prioritized and personalized weights preferences on paths, which are important for real applications. For instance, for mining user characteristics and crafting recommendation explanations. One limitation of the previous method is that metapaths are not able to characterize rich semantics. For example, if we think about the relation two users both buy and review the same product, this relation cannot be depicted by a metapath. To solve this, Zhao et al. Designed FMG by replacing the metapath with the metagraph, as the ones in this slide, to capture more complicated relations between entities in an heterogeneous graph. Next, they use factorization machine to fuse the features of users and items across different metagraphs for computing the final preference score for an item starting from a user. And metastructure-based methods overall are explainable since these manually designed metastructures provide the reference for the recommendation, for instance, by matching the metastructure between the candidate item and the interacted item or the target user. We provide here additional methods following this strategy, which we do not delve into them due to the time again. The metastructure-based methods are easy to implement, and most works are based on matrix factorization techniques with relatively low model complexity. However, the selection of metapaths or metagraphs requires domain knowledge, and these metastructures may vary significantly for different datasets. Moreover, it may not be suitable to apply the metastructure-based method under some specific scenarios. Let's say, let's consider, for instance, a news recommendation task where entities that belong to one news may belong to different domains, which makes it difficult to design metapaths. One issue in the metapath-based methods, in the metastructure-based methods, is that the connection patterns are not explicitly modeled, which makes it hard to learn the mutual effects between the user item pair and the connection pattern. So recently, path embedding-based methods have been proposed to explicitly learn the embeddings of connection patterns. The solution encodes the connection patterns between user and item pairs or item-item pairs into vectors, which can be then integrated into the recommendation framework. Let's see a few example methods belonging to this class that we will also cover in the hands-on with Giacomo later. As the first example, real-world knowledge graphs are usually huge. So enumerating all the paths between a user item node for similarity calculation is usually computationally expensive. And to solve this problem, Xian et al. Proposed a reinforcement reasoning approach over knowledge graphs for explainable recommendations. The key idea is to train a reinforcement learning agent for path finding. And in a training stage, the agent starts from a user and is trained to reach the correct items with high rewards. And in the inference stage, the agent will thus directly walk to correct items for recommendations without having to enumerate all the paths between user and item pairs. Café instead presents an approach to complete KGs based on evaluating candidate triples using a set of neighborhoods-based features. Under this course to find paradigm, they present a corresponding method to approach the problem of KG reasoning for recommendation. And as we see in the figure, given a KG, a user profile is first composed to capture prominent user-centric patterns in the core stage. And to conduct multi-op path reasoning guided by the user profile, they decompose the reasoner into an inventory of neural reasoning models. And in a final stage, the selective neural symbolic reasoning modules are composed based on the user profile and then are exploited by a profile-guided path reasoning algorithm similar to the ones we explained previously to efficiently perform batch path reasoning for recommendations. So finding right paths to reach the correct items for a given user. However, existing methods are coarse-grained in relation modeling, and so One et al. Further develops this research direction and presents one next step across this line and with a model called knowledge graph-based internet network, KG. It consists of two key components: the user intent modeling, which uses multiple latent intents to profile user item relationships and formulates each intent as an attentive combination of KG relations. Meanwhile, also encourages different intents to be independent of each other. And then we have relation path-aware aggregations, which highlights the relation dependency in long-range connectivity, so as to preserve the holistic semantics of relational paths. The last one we see, very recent, it considers the model proposed by Shinji et al. That is specifically a novel path language modeling recommendation framework that uses a language model over KG paths consisting of entities and edges again. So given a knowledge graph, they extract training path sequences under different op constraints. And by leveraging augmentations for features with similar semantics, they achieve a series of training data sequences. Then they adopt a transform-based encoder to train an auto-aggressive path language model. And then they use this model in the recommendation pipeline, which includes all the steps starting from sequence construction, the training of the model, the path generation, and the recommendation step. You see here that there are the path embedding-based category includes a really vast set of methods. We invite you to delve into the other existing ones offline after this tutorial, and you can see that they are a lot. And this category is really the most prominent currently. The path embedding-based methods encodes as advantages. We can consider that encode the connection pattern of user item pairs or item-item pairs into latent vectors, which makes it possible to consider the mutual effects of the target user, the candidate item, and the connection pattern. In addition, most models are able to mine the connection patterns automatically by enumerating qualified paths and selecting salient ones without the assistance of predefined metastructures. Therefore, it is likely to capture expressive connection patterns. However, the number of possible paths in the graph can grow to a large number if relations in the graph are complex. And in reality, it's really impossible to exploit all the paths for each entity in a large-scale KG, which may hinder the performance of the model. Let's briefly compare the metastructure-based methods and the path embedding-based methods. So the connection-based methods really relies heavily on the connection patterns. However, the representation ability of the meta path is limited, which hinders the performance of traditional metastructure-based methods. Path embedding-based methods further overcome another shortcoming of metastructure-based methods, that is that domain knowledge and handcrafted paths are required. These methods enumerate possible paths and explicitly model the relations between user item pairs and item-item pairs. However, the scalability is sacrificed to some extent in the path embedding-based methods, since these models are relatively complex and more computations are required in enumerating paths and learner representations. We conclude our overview with propagation-based methods. Embedding-based methods leverage the semantic relations in the KG to enrich the representation of users and items, or to regularize the recommendation. But it is difficult for them to capture high-order relationships between entities. Then we have seen connection-based methods that use the connectivity information in the graph to get the recommendation. However, it is avoidable to lose information by decomposing the sophisticated user item connection patterns into separate linear parts. And so, to fully exploit the information in the KG, propagation-based methods have been proposed to integrate both the representation of entities and relationships and high-order connection patterns for, let's say, reaching a more personalized recommendation. And these methods refine entity representation by aggregating embeddings on multi-hop neighbors in the KG. The challenges to face when adopting propagation-based methods include how to assign proper weights to different neighbors, how to propagate messages on different relation edges, and how to improve the scalability of models. And we subdivide this category according to which type of entity is refined in the message propagation procedure, either the user entity, the item entity, or both. Let's briefly start with methods refining the user entity representation only. Wang et al. Proposed RippleNet that first introduces the preference propagation mechanism in the KG. RippleNet takes a user U and an item V as input and outputs the predicted probability that user U will click item V. For the input user, his historical set of interests V is treated as seeds in the KG, and then extended along links to form multiple ripple sets. A ripple set is the set of knowledge triples that are k-hop away from the seed set V. And these ripple sets are used to interact with item embedding, the yellow block, iteratively for obtaining the responsive of user U with respect to item V, that is the green block. And they are then combined to form the final user embedding, that is the gray block at the end on the right. And lastly, they use the embeddings of user U and item V together to compute the predicted probability Y that a user will click on a given item. Tang et al. Proposed a key PM with a similar preference propagation mechanism as in RippleNet. The difference here is mainly that this model uses entities derived from transR, another embedding-based method. And then this model also applies the self-attention mechanism to assign the weights for entities in the aggregation process and to concatenate the user relation representation obtained in each layer. The above, let's say, the works that we previously mentioned have refined the user representation by aggregating entities in the neighborhood of the user. Another solution is to learn high-order representation of the candidate item by aggregating embeddings of its multi-op neighbors. In this way, the representation of the candidate item contains information from h-op neighbors. Wang et al. In this area proposed KGCN, in which the weight of each neighbor is user-specific for the items. And briefly, given that the previous model was prone to overfitting, Wang et al. Proposed a follow-up approach that is KGCN-LS, which further adds a label smoothness regularization on the model to avoid overfitting or to reduce overfitting. And recently, some papers have also explored the propagation mechanism in the user and both users and items in the KG. Again, by using their neighbors. So in this case, we refine user and item representations by considering both the neighbors of both. Two main examples here. The first one is KGAT, which directly models the high order relations between users and items with embedding propagation in an end-to-end fashion. This model framework consists of three main components: the embedding layer, which parameterizes each node as a vector by preserving the structure of the KG, an attentive embedding propagation layer, which recursively propagates embeddings from a node neighbors to update its representation, and employ knowledge-aware attention mechanisms to learn the weight of each neighbor during a propagation. And finally, we have the prediction layer, which aggregates the representations of a user and an item from all propagation layers and outputs the predicted matching score. One limitation of the previous approach is that it may introduce irrelevant neighbors in the propagation process. And to overcome this issue, Shah et al. Proposed AKG, which learns enhanced representation of the user and the candidate item by propagating information in a subgraph of this user item pair. This framework is composed of three modules: the subgraph construction that automatically constructs the expressive subgraphs, that is the link, let's say that link the user and item pair to represent their connectivity. So we limit the connectivity to this subgraph. Then we have the hierarchical attentive subgraph encoding. So the subgraph is further encoded via a hierarchical attentive embedding learning procedure, which first learns embeddings for entities in the subgraph with a layer-wise propagation mechanism, and then attentively aggregates the entity embeddings to derive the holistic subgraph embedding. And then we have the preference prediction with these learn embedding, the embeddings learned in the previous steps. We use nonlinear layers to predict the user preference towards the item, as usual. These are other two models we invite you to explore after this tutorial. So we finally summarize the main advantages and shortcomings of different propagation-based methods. Propagation-based methods are usually computationally costly. As the graph grows larger, it becomes difficult for the model to converge. To improve the efficiency, fast graph convolutional operations have been proposed. And another technique is to apply neighborhood sampling in each layer to solve this problem about efficiency. However, the random sampling will inevitably lead to a loss of information, failing to fully explore the knowledge in the graph. Here, for your future interest, we recap the adopted taxonomy in this tutorial and the mapping with the representative methods belonging to each class that are often used as also baselines among each other in the papers we have surveyed. So to conclude this part, we provide a qualitative comparison of methods across category. And we start with the embedding-based methods. Sorry. That are the most flexible and relatively easy to, and with them is relatively easy to encode the KG with the KGE module. The learn embedding can be naturally incorporated into the user representation or item representation. But we should also consider that in comparison with the other methods. So differently from embedding-based methods, for instance, connection-based methods, in them can be tedious to define metapaths or metagraphs in the graph. And in propagation-based methods, the aggregation and update part need to be carefully designed. So this is an advantage of embedding-based methods. Moving to connection-based methods, metapaths are usually diverse for different application scenarios. It's hard to define metapaths and apply the metastructure-based method. And the quality and the quantity of paths are crucial for connecting-based methods. Both the path embedding-based method and the propagation-based methods are inappropriate in case of large-scale datasets. Let's say because the computational complexity may grow large in enumerating all the paths and neighbors that we consider during the optimization. And finally, we have propagation-based methods, where both as well as connection-based methods. Also, these propagation-based methods can be interpreted with paths in the KG that we can use also to derive the explanations, as we will see later. And they also tend to fully explore the relationships between users and entities in the KG with respect to the other two methods. So now we have, if there are questions, we can answer them. And in the meantime, we can move to a break of 10 minutes. So we can resume at, we will change this at 1.
Hi, I have a question, please.
Yes,
What
sure.
knowledge does a propagation-based method suppose additionally to the others?
Okay, great. Thanks for the question. I will go back to the slides such that I can use. So the idea is that with usually with the other methods like embedding-based methods or the ones based on path embeddings, you used the specific embedding associated to a user or an item. With propagation-based methods, you enrich these methods, these embeddings, these single embeddings with knowledge about the neighbors of the considered user or the considered item. And you do this by aggregating the embedding of the current user or item with the embeddings of the neighbors. And this combined embedding can be is being proven to provide to result in better performance of the recommendation mode. So the main added value of propagation-based methods is the usage of the neighbors of a given user or a given item. Does it answer?
Yes, thank you.
Okay. Are there any other questions? Okay, so we will be also happy to answer questions later on offline during the conference with Ludovico and Giacomo or with me in the chat. So now we move to the break and we will be back in around 7 minutes. Thanks. Giacomo, I will stop sharing. You can share.
Okay, so since we are already a bit late, we need to start again with the second part of the handbooks and of the answer. So here you can find the QR code of the notebook. I saw that someone in chat got a lot of problems with the permission of the files to write, and someone of you got some problems writing the files or something like that, executing. So I will advise to see how we run the notebooks and then download the material later, because maybe there is some problem with the drive folder and you cannot write or write files. Okay. Okay, so we move now to the part of the methods. The second hands-on is about GDPR, which is a policy-guided path reasoning method, which is a self-explanatory method. Also, you can see something about GDPR in this image that tries to use the knowledge graph to create paths which can be used to then create explanations via templates.
Giacomo, are you sharing?
Oh, maybe not. Let me check. One second. Yes. Yes. Good. Yes. So the QR code for the collaborator is different. Okay.
It's a different one than you shared before.
Yes, because we have four notebooks, but you find it in the you can find it in the folder. So if you have already scanned the code the first time, you should be fine just from the Google Drive folder. So let's go back to notebook. Okay. So in the first part, we loaded, visualized, and preprocessed movements, Last.fm, and Amazon cell phones. We also saw how to load their knowledge graphs and to perform some preprocessing both of the dataset and the KG. Also at the end, we save the dataset and the KG in the standard format. From there, what we are going to do is to map these datasets and KG in the standard format to a PGPR readable format. PGPR, since we use the entity, needs to have them grouped by type, so it needs to perform. We need to perform an additional mapping. Then we will train the Transy embedding, which is a translating embedding that we will see more in detail later. And then we will train the agent to learn the policy. And finally, we will extract the path from the learner policy. So as first, we can import our packages, in our case, only gzip. Of course, when you start with a new notebook, you need to mount your drive again and browse the folder. So let me do that. Okay, so before going directly to the method, let's see some prerequisites that we need to understand. Here you can see some theory that we have that Mirko already discussed before. You can see also the references with some GitHub repository. In general, PGPR it's a model that belongs to the family of path reasoning methods. So they're aiming to construct the paths step by step and to produce recommendations associated with reasoning paths. So let's see an overview of a path as an explanation. Here you can see a path which can be extracted. For example, user A watched movie A starring -1, which means the reverse relation, which is a passive relation in this case, and actor A starring, which is an active relation, movie B. As you can see, this path starts with a user and ends with an item. This is the crucial part. We need to focus on paths that are user-centric. They are called user-centric, that start from a user and end from a movie. In order to select only these type of paths, what is done, as we have already talked before, we need to define meta paths. Why we need to define meta paths? Because of course there might exist a lot of different type of paths. Here you can see an example. This path starts from a user and ends up with a category. We cannot use that to perform a recommendation nor an explanation. Here you can see also something to note here is as well that this length doesn't consent us to reach any product because the movie is connected only to external entities, so we cannot find any product. The second example shows a path that starts from a movie and go through a category, and here again we cannot perform a recommendation. So meta path, we can say that is a relation sequence. Is a relation sequence that connects two entities, and these meta paths are used as rules to constrain our search in the knowledge graph. So another thing to know before going with the PGPR training is the Transy embedding. So Transy embedding is just one of a very large group of knowledge graph embeddings. Transy is very famous. And what knowledge graph embedding aims to do is to reduce the knowledge graph in a low dimensionality space, trying to representing their semantic meaning. Here you can see an example of a knowledge graph which have only two relations, and you can see how the Transy learns during this process and separates the entities based on the relations with a predicate. So the Transy is crucial for PGPR because it will be used for two main functions. The one is the multi-op scoring function that will be used to construct the path step by step, and the reward function that will be the one that make the model understand which is the best policy. So let's start now with the PGPR. So PGPR is self-explainable, as I said, and is based on reinforcement learning. As a reinforcement learning model, we need to define 4 things: environments, which is our knowledge graph, the set of states, which are the node of the knowledge graph, and the set of actions, which are the edges, which are the out edges of the knowledge graph given a particular state, and the reward, which is computed using tracing. So here, for example, just to give you a better understanding, if you are in the state, so the environment is called the KG, state A, user A is the state, and as you can see, the action that we have is purchase to go to item A, or we have mention to go to feature A, and etc. What PGPR aims to do is to start from our user and construct step-by-step path that brings to an item that can be recommended. Okay. So here we have the architecture of PGPR, and we will go through the main components. So the first one is the KG environment. As I said, we need to transform the knowledge graph into a state action space, and this is done in the KG-env file of PGPR. Then from the state, what is done is to compute our pruned action space. So since we might have a lot of outgoing edges, and this might be computational impossible, we need to cut down the actions that we can take. And this action will be used to construct the path step by step. Then when we reach a product, for example, if we have started with the user and we have reached all the way until this product, we will compute a reward that will be given as a feedback to the policy value network. So at the end, when we will have the policy value network which is trained, the policy value network will give us this policy, the policies represented by pi, will give us what is the probability of the action of the agent taking that action, given that current state and the action space, which is this capital A. From there, what is done is to construct the paths. And here is the real policy guided, because you start searching for paths and you perform a beam search and composing the path using the probabilities that you have found from the policy. Okay, so now that we have some prerequisites, let's start with the notebook itself. So we start loading, we start setting the data set. And the first thing that we need to do is to create a train set split. And we do that using our module, which is the mapper, and it will write the train set split for the dataset. In this case, we are using a time-based, user-based split. So this means that the interaction are sorted by timestamp, and we take the first 80% as the train set and the last 20% as test set, and they are the less recent interactions. So after that, what we do is to yes, we have already done that. Is to oh no, okay. Now we have just imported, so we need to do that, and then we can move to the preprocess. We can see what this file has created, what this function has created. Okay, as you can see, he has created a lot of files which are based, which are belong to 2 families. One are the entities, as you can see, actor.txt, or for example, category.txt, and they contain all the entities of that type. How this is done, they are inferred by the relation. If, for example, I have a triple, which has a relation belong to, I know that the entity head is a movie and the entity tail is a category. So in this way, we group all the entities, and we group also the relations. For example, category, product to category. Okay. Here you can see an example of the training set also. And you can see that the training set is written as the UID, PID, the implicit feedback, so in this case is 1, and the timestamp of the interaction. Okay. So, so here we will compute the the mapper to PGPR. So the structure that we saw before, in reality, it was there because it was already computed. That will be computed by the map to PGPR file. So the entities and the relation files will be created by this map to PGPR. We have already everything in the folder, so of course, running the ls, we see all the files. And here, to give you an example, let's take the editor entity file and let's see how it's composed. We have the new ID and the name, which is the old ID of the editor in the knowledge graph that we have in the standard format. To see an example, let's see also a relation, and you can see that how is the structure. So every row number represents the product ID. So row 0 means product 0, and these are the relations that the product have with the categories. Because we are in the belong to file, so category, product, category. So these are all the categories which are linked to the row 0, which is the product 0. Okay, now what we need to do is to run the PGPR preprocessing. This will create objects that will be used by the model later. So it will create a knowledge graph object and a dataset object that will be stored. As you can see, is loading the entities, creating a knowledge graph, cleaning, and making all the computation that it needs to do. The files are created.
Sorry for interrupt you. There is a question in the chat.
Yeah.
Was for a point that you mentioned at the beginning. How big can the action space get here if each item is a node in the graph?
Okay, so it depends by the dataset. If the dataset has a lot of outgoing edges, you might find out you might have a lot of possible actions, and this depends by the density of the graph. And you need to perform a pruning, which is already implemented in PGPR, and we performed that with 250 actions. But it depends by the dataset, and you can tune also the pruning based on that. I hope this answers your question. Okay. Do I close the chat? Okay, done. Okay, so as I was saying, these files will be created in the preprocess PGPR 10 folder, and as you can see, these are the classes that I was saying: the dataset.pkl, the kg.pkl, and also we have the transembed, the transembed. No, the transembed. We are going to train it now. So the next step to do now that we have the dataset in the right format is to learn the transembeding. So the representation of our knowledge graph in the translated space. So this can be done running the train transc model .py, and these are the main hyperparameters. So we have the epochs, batch size, learning rate, which are pretty standard, with the K for Adam, and all the parameters are pretty standard. The only one which are particular are the embedding size, which defines the size of the knowledge graph embedding and the number of negative samples. So what is done usually to regularize this type of embedding is to create false triplets to make the model more robust. So you can train the transient running this cell. I will show you, but you don't need to run it now because it takes approximately 1 hour with my GPU. And so I don't know how much does it take with Colab. So at the end, it works, I guarantee you. You will have this transient model as the epoch 30, in the case we have specified 30 as epoch. And this will be the representation of our knowledge graph. From there, we can move to the next step, which is the training of the agent. And what is done? So what is done is to start with an empty state and randomly sample a user. So the agent will always start from a user and will firstly evaluate all possible valid actions, so all the outgoing edges, and based on the multi-op scoring function, we'll sort them from higher to lower. And from there, we generate multiple paths at the same time. As you can see, the multi-op scoring function is composed by the embedding multiplication between the entities that compose the path. For example, if we have a path of len 1, we are just doing the multiplication between the entity head and the entity tail. And we will add every time the embedding from the new piece of path that we are creating. Then we repeat this previous step. So at the step 0, we have a path of length 0, at the step 1 of length 1, etc., until we reach the length which is desired. In our case, is 4. So when we and the other thing that we want is to reach a product, and then we will give the reward to the policy, and this is done computing the transient embedding the product between the entity 0, which is the user, and the product. So this is pretty much the relevant score between the user and the product. Okay, so at the end, the policy will store the probability of taking the action, and then we will use later to learn to extract the paths. So here you can see the parameters of the train agent, and here you can specify, for example, the max number of action, as they asked in chat before, and the max path length, which in our case is 4, and this thing depends by the metadata that you meta paths that you define, of course. Then we have the gamma that defines the exploitation value, and also we can drop out some actions and have a state history, which means that we are considering also some information about the previous states. You can train the agent running this. It's common, and as you can see, your agent will start to train, but we don't need to do that now, so we will stop this training. Okay, so the files will be created also in TMP, train agent, and you can see that the final file will be policy paths epoch 50. This is our policy. So from there, what we do is to extract the paths from the policy. So what we are going to do is to perform a beam search. If you're not familiar with that, what is this image can help you understand the concept. So we will start composing the path, starting from the user. We evaluate all the possible actions, and this score is the score given by the policy, so the policy that we have already learned. And what we do is to take the first Z1 elements and simultaneously build new paths. Okay, and every one of these will recursively do the same thing. So we are building multiple paths at the same time, and at the end we will have a complete path. For example, you can see this. User A watched movie F being watched by user U watched by movie P, and this is the final path that will be stored. This is the hyperparameters for the test agent, and here important parameters can be the top K, which is the number of samples that you take for every beam search. For example, Z1 determines how much you take in the first state, how much in the second, and in the third one. This parameter is very important because we try to use GDPR with eigenvalue of this parameter, and it will produce a lot of paths and can be very useful if you need to perform post-processing, for example. So we can run the test agent from here, and of course it doesn't work because I can't run it. Okay, so at the end we will have the our paths, which is policy paths epoch 50. Okay, and this is all for PGPR. So to summarize, we run our mappings, and we can run the preprocessing of PGPR, then train the agent, and then test the agent to extract the paths. So now we will move to the other method, which is Café. So a lot of concepts that we have seen in PGPR can be applied also in Café, which is cost-to-find neural symbolic reasoning. So here again, we will mount our Google Drive, and we can start. So this model doesn't rely on reinforcement learning. nor the policy. So it does something similar, exploiting the neural symbols. So, okay. So let's start from the architecture. So here you can see that it's composed by these two main parts, let's say, because the first one is the knowledge graph. And the first part is the user profile of UI, which is a group of what's done is to find meta paths which are more prevalent for a particular user. For example, the model starts a search and try to understand to weight which meta paths is more useful for a particular user. For example, a user might be more prevalent to watch movies which are related by category or by editor or by writer, for example. So this step will try to learn the user profile and will weight which meta paths are more useful for a particular item. Then we have the neural symbolic reasoning modules. So in PGPR, we had just one reasoning step, which was done by the agent. Here we will have multiple reasoning modules, which are dependent by the user profile. And we will take the most relevant one and discard the not relevant. And then using these learn neural symbolic modules, we can extract the paths, doing something similar with this profile guided path reasoning. And this will exploit a layout tree structure to be more efficient and also to exploit the user profiles that we computed before. Okay, so in order to run this model, what you need to do is to compute the trans-C embedding, but since we have already computed with PGPR, we can use that. So we will just move the file in the folder. And the second thing that we need to do is to map the dataset to Café. And as I said before, these methods needs to have the entities and the relation grouped by type. So it will do the same thing. Here you can see the structure of the file that has been created by the map to Café. And here is interesting to note that we will have the KG rules explicitly defined, and this is very useful compared to PGPR when you need to define from code the meta paths. Here you can set up the relations and the meta paths directly from a file. So then to run Café, we need as well to do a preprocessing. So similar to PGPR, we need to run this preprocessing. The preprocessing of Café takes a long time, approximately 1 hour, because it builds the user profile modules. So the profiles are learned in this part. Then, when we have the user profiles, we are ready to train the neural symbol, and we will train the neurosymbolics modules, but I put also a description of the user profile composition here, if you're interested. So the neurosymbolic reasoning modules will be learned using this prominence score, which tells us how much a path pattern, in this case is referred with P, is valuable for a particular user. And then the neural symbolic reasoning model will perform a heuristic search to find the profiles. Then every module relies on the reasoner. So every of these modules rely on our user profile and the type of the user profile, and take part in the reasoning process for that particular pattern. So finally, to train this neural symbolic, here you can see the code and the hyperparameters. We have the embedding size and the deep module and all the other parameters are very standard. Something that to note is that you need to decide ahead which top K you are going to produce, which reduce the flexibility of the model compared to GDPR when you can compute top K of different size. Here you need to predefine which size you want. So here is the learning, but of course I will stop it. And finally, the last part is the extraction of the paths. So we will use the layout tree to extract the paths. And this is done running the execute neural symbol using the do infer as true. And when we run this, we will obtain the final paths. Okay, so that's it for this part. Hope that you understand the main parts, and also I will encourage you to check the notebooks offline because I think it's enough detail to understand all the parts. And also with this guide, you will be able to also run the models by your own and also use our pre-trained. So without further ado, I think we can move to the other part if Mirko is ready.
Yes, thanks, Giacomo.
Okay, so I should stop the, okay.
Yes, thanks.
Sir?
Yes. Yeah, sure. Okay.
I was reading it, I didn't quite understand.
Which one, sorry?
Yeah.
Okay, okay.
Can you give
Yes.
two sentence somewhere?
Yes, yes. So this task is a task where we are using the knowledge graph, an integer k. Yes. So we use. Okay, okay. So the question is, can you elaborate about the KGRE task, rec task? And I was saying that this task is the task of producing recommendations and paths. So analyzing the definition is given a knowledge graph, which is the set of triplets, and an integer k, which represents the maximum size step that we want. So how much longer the path we want to construct. The goal is learning to learn a model, in our case, GDPR or Cafe, that takes the users, the products, and the paths. And we produce an estimate of 1, the relevant score between the items, which is done by Transc in our case, because we use user product score, which is this one, and a probability, which is the policy in our case, and LOP is the path. That path is followed to reach the particular product. Yes, I forgot to put the description of the variable, so I will add that. Yes, sorry. LK is the set of all paths of size K.
So F is the relevant product you can use.
Yes, F is the product with the Transc embedding. This current function. S is the probability of the path UP, which means start with U and end with a product. Start with a user and with a product. It's the probability of the agent taking that path, and is given by the policy. Okay. You're welcome. Okay, so I can stop the sharing. And Mirko, if you are ready.
Yes.
Shall I move to
Can you see the screen? Giacomo, do you see the screen?
Yes. Let me.
Okay, great. Thanks, Giacomo. So in this last part, given that we have seen methods and so on, we provide a short overview of works that are relevant from the perspective of the explanations evaluation. So in general, it could be desirable if an explainable recommendation model can achieve comparable or even better recommendation performance than conventional non-explainable models, and meanwhile achieve better explainability. To evaluate the recommendation performance, we can adopt the same measures as well evaluating conventional recommendation algorithms. For instance, for rate prediction tasks, we can use mean absolute error or root mean square error. while for top-end recommendation, we can adopt standard ranking measures such as precision, recall, F-measure, and normalized discounted cumulative gain, as you would normally do with the other recommendation models. We can also conduct online evaluations with real users based on online measures such as click-through rate and conversion rate, which are frequently used to evaluate ranking performance. There are also plenty of other properties that should be considered while providing recommendations to users, such as their explainability, novelty, diversity, and so on. In this part, we mainly focus on the evaluation of explanations. Similar to the provided recommendations, explanations can also be evaluated by directly involving users in user studies or online in a real setting, or considering users indirectly offline, such as by using collected interaction datasets and knowledge graphs. Usually, offline evaluation is easier to implement, since online evaluation in user studies would depend on the availability of data and users in real-world systems, which are not always accessible to researchers. As a result, online evaluation is encouraged, but not always required, especially in the first stages for explainable recommendation research. Offline evaluation would be preferred in that case, since it can be used to narrow down the set of explanation models to test with users in a cost-effective way. And I should say something that we will not cover a comprehensive survey of the different techniques for evaluating the explanations, and I would like to invite you to see these two surveys that you see below for more details about a full comprehensive landscape of how to evaluate explanations. So a straightforward approach to evaluating explanations is through user studies based on volunteers or paid experiments subjects. The volunteers or paid subjects can be either directly recruited by the researcher or recruited through online crowdsourcing platforms such as Amazon Mechanical Turk and Cloudflower, for instance. Usually, the study will design some questions or tasks for the subjects to answer or complete, and conclusions will be derived based on the responses of the subjects. Let's see some examples of works that adopted an evaluation based on a user study. For example, as also Ludovico showed, Erlocker et al. Studied the effectiveness of different explanation styles in user-based collaborative filtering. In this research, the study was performed as a survey, and study participants were presented with the following hypothetical situation. Imagine that you have $7 and a free evening coming up. You are considering going to the theater to see a movie, but only if there is a movie worth seeing. To determine whether there is a movie worth seeing, you consult MovieLens for a personalized movie recommendation. So MovieLens recommends one movie and provides some justification. Each participant was then provided with 21 individual movie recommendations, each with a different explanation component, and was asked to rate on a scale of 1 to 7 how likely they would be to go and see the movie. And then the subject's average responses on each type of explanation were calculated to evaluate the effectiveness of the different types of explanations. In a slightly more recent study, Vig et al. Conducted a user study for 4 explanation interfaces based again on the MovieLens website. Subjects were asked to complete an online survey in which they evaluated each interface about how well it helps them to understand why an item is recommended, decide if they like to recommend that item, so the effectiveness component, and determine if the recommended item matches their mood, so mood compatibility. The survey responses helped the authors to conclude that the role of tag preference, for instance, and tag relevance was important for promoting justification, effectiveness, and mood compatibility with respect to the recommendations. Besides large-scale online workers, we may also conduct user studies with relatively small-scale volunteers, paid subjects, or manually labeling the explanations. In this sense, Ren et al. Took a random sample of 100 recommendations and manually evaluated their explanations regarding the accuracy of sentiment labels, which helped to verify that the proposed viewpoint-based explanations are more informative than topic labels in prior work in their specific study. As another example, more recently, Wang et al. Recruited participants through Amazon Mechanical Turk to evaluate with a diverse population of users at events a range of explanations. And the study was based on the review data in Amazon and the Yelp datasets. For each participant, the authors randomly selected a user from the dataset, one of the between Amazon and Yelp, and shown these users' reviews to the participant, so that the participant could get familiar with the user. And then participants were asked to infer the user preference based on the reviews that they saw. And finally, they were asked to evaluate the recommendations and explanations provided to the user by the testing model by answering several survey questions from this user perspective. So as you can see, we have a broad range of different techniques to evaluate explanations. And moreover, except for textual explanations, user studies were also conducted to evaluate visual explanations. For example, here Chen et al. Generated visual explanations by highlighting image region of interest to users and leveraged Amazon Mechanical Turk to hire freelancers to label the ground truth images for evaluation. So in this case, the crowdsourcing platform was used for the labeling, not really directly for the evaluation of the explanations. Another approach to evaluating explainable recommendations is through online experiments. Online evaluation and user study, in fact, might be concurrently performed. Sometimes user study can be performed in online platforms, however, they also have significant differences regardless of the operating platform. And user studies usually ask participants to complete certain questions or tasks under given experimental instructions. And as a result, is really important, participants usually know that they are being investigated. With on-file evaluation instead, such as A/B testing, usually the selected users are exposed in the real experimental environment without their knowledge, so unconsciously. And the platform collects user behavior to study and compare the effectiveness of different strategies. Now let's see an example of online experiments for evaluating explanations. Zhang et al. As an example, conducted online experiments focusing on how the explanations affect user acceptance. The author conducted an A/B test based on a commercial web browser, which had more than 100 million users with 26 monthly active users. So was active as a website. The experiments recommend compatible phones when a user is browsing mobile phones in an online shopping website. And to evaluate the explanations, 3 user groups were designed, including an experimental group that receives the testing explanations, a comparison group that receives the baseline people who also viewed explanations, and a control group that receives no explanation. And the click-through rate of each group was calculated to evaluate the effect of providing personalized explanations. In general, moving to the last category, there are 2 approaches to evaluating recommendation explanations offline. That means without directly involving the users. One is to evaluate the percentage of recommendations that can be explained by the explanation model, regardless of the explanation quality. And the second approach is to evaluate the explanation quality directly somehow. However, we have to note that more offline evaluation measures and protocols are here to be proposed for comparing explainative evaluation. And here we are just providing a few examples. For instance, for the first approach, Abdullah and Azuri adopted mean explainability precision and mean explainability record. More specifically, explainability precision is defined as the proportion of explainable items in the top end on a recommendation list relative to the total number of recommended items for each user. On the other hand, Explainability, recall, is the proportion of explainable items in the top and recommendation list relative to the total number of explainable items for a given user. Wang et al. Proposed a fidelity metric to evaluate explainable recommendation algorithms. And again, this metric was defined as the percentage of explainable items in the recommended items. For the other approach, I would like to provide an hint towards our recent CGIAR paper, where we conceptualized 3 novel properties that model the quality of explanation paths that are used to generate the explanations. The first perspective that we will see here is related to the recency and of the linking interaction that we use in the path. And the assumption is that the recency of the linking interaction presented in the reasoning path matters. In particular, a recent linking interaction, for instance, can help the user to better catch the explanation, while older interactions might not be perceived as valuable or not remembered. Here on the top, you can see a timeline of user interactions sorted from less to more recent. For this user, a candidate recommended product, the silent of the lamps, for instance.
Okay, we probably run into a technical problem. Let me check. Okay, so Mirko's laptop has had a slight issue.
Okay, so I will continue this part. I will continue this part for Mirko and his laptop because this laptop has died. So we will talking about the linking interaction recency. So when considering user timeline of interactions, there might be interactions that are more recent. Huh? Oh, okay. Sorry. It's fine now. Considering these users interaction timeline, you can see that of course the user have interacted products in different times, and what can be done is that there might exist products that can be explained using multiple explanations. For example, the silence of the lamp can be explained using 2 different parts. One is based on the linking interaction, the gladiator, so based on a previous interaction with this movie, and one based on the old interaction with the Breakfast Club. So when we have this choice between 2 parts, the idea here is to show the one which is more with us a recent interaction which is more recent. The other property instead is the shared entity popularity. So we consider the shared entity, the external entity which bridge which act as a bridge between the previous interaction and the recommended product. Here, for example, you can see get used on Ana Maria Quintana. The idea here is that this shared entity can help to provide context to the user. For example, if a user receives a recommendation of an item that doesn't know, the shared entity might help him understand if the movie can be of interest or not. So the idea is that a popular shared entity is more likely to be known by the user and consequently can help to provide context. Here in the example, you can see that if we recommend Almost Famous and we have 2 paths, one based on Get Houston and one based on Ana Maria Quintana, according to this metric, we can choose the one based on Get Houston, which is more popular and is more likely that the user knows that actor. And the popularity is based on the degree. So how many relations, how many relation that entity has with other entities, which means in the case of an actor, for example, the degree tells us how many movies as an actor starred. Finally, the diversity of the path type is considered for a group of explanations. For example, if we have this top K, we can see that the different colors represent different path types, and the path types are defined by the type of the entity. For example, we can have director, producer, etc. And we provided a measure to understand how many relations are present in the top K. And this can be useful because the diversity is known to help human understanding, and also to provide more surprise and long-term engagement. And yeah, so as a summary of the evaluation metrics, a desirable explanation recommender model will not be able to provide high-quality recommendations, high-quality explanations, because there is a trade-off between these two properties. And also, explainable recommender model would be evaluated in both perspectives. Finally, the quantitative methods include online, offline, and user studies approaches. Qualitative evaluation is usually implemented by case studies over the generated explanation, and is very useful to make people understand what the explanation looks like. This is very useful also when we are doing papers. A lot of papers about explainability doesn't show what is the explanation that is provided, and the case study can help to better visualize the explanation. Okay.
Okay, just to let you know, we're sorry, we are like 15 minutes late. If we're all fine, we continue since this is the last question, but we wanted to let you know that, I mean, we were supposed to finish now, but we have 50 more minutes and then we're finished. We are done, okay? Sorry for the delay, just wanted to let you know.
Okay, so let's move to the last and so on part. And so again, you can find this Jupyter notebook in the folder. And the fourth one, it's about generating the explanations and evaluating the recommendations. Oh, sorry, second. So the third one is the CAFE, so cost to find. The second is PGPR. A second. Okay, yes, of course. So third one. But let me know if the link is working. It's working for your, this link is working. Works? Okay, lovely. Okay, so just to recap what we have done in the previous notebook, we have trained and produced the explanation paths for the CAFE and for the PGPR model. So now what we are going to do is to use this produced path to create top case of recommendations and to evaluate the recommendation produced. And finally, we will translate the paths into textual explanation and see what they look like. Okay, so as first, let's import our modules, and we will start creating different dictionaries that we will use to store the data both of the PGPR and the CAFE, and this will be useful to make the comparison later. Also, we do that both for the top case, for the train and test labels that we will be used in the evaluation, for the metrics, and then we define the metrics. Here in particular, we will use NDCG, the recall at K, and the precision at K. So we will further see more about these metrics, but for now, just run the code. Then, as you have seen previously, the paths are composed by the entities, and the entities are not in plain text. They are, of course, stored as a ID. So we need to convert them, and to do that, we can use our function entity to plain text from the knowledge graph utils, which will return a dictionary that maps the entity ID to the plain text of that entity. Then we'll use a function, which is the template function. So the paths are usually transformed in textual explanation using templates-based methods. So what is done is a template is pretty much a string of text which is composed by placeholders, and we can substitute the entities of the paths with a placeholder to generate recommendations. We will say more later. For now, let's just run the code. Okay, so as first step, we need to load the paths. And we will start with PGPR and we load the paths of PGPR. So here we can load the paths. As you can see, it takes 26 seconds, and we visualize them as first. So after that, what we are going to do is to map create a dictionary that contains the UID and the PID and the paths. Here you can see what the predicted paths looks like. So you have UID, PID, path score, which is defined by the user product dot product, and then the path probability, which is defined by the policy, and then you have the path itself. So as you can see here, that's why we need the placeholders, because for example we have user 0 or for example product 953. We need to map that to a real name. So so in the next shell, what we're going to do is just to group the predicted path by user and product. Something to notice is that PGPR is able to create multiple paths for the same item, and this is also the reason why we need to select the best path for a particular user product. And we are going to do that now. So so here what I'm doing just to visualize the mapping, which is taking a random user, a random product, and showing what a path looks like. And this is done to show you that this user and product have multiple paths. For example, you can see that there are multiple paths. So for the top N generation or top K, what we need to do is to load the train labels and test labels. In particular, we are assuming that we are not going to recommend products that the user have already interacted with. So we use the train labels to discard them, and the test labels, of course, we use that to evaluate. So as I was saying before, we need to select the best predicted path. So for every UID and PID, we will choose the path with the maximum probability, which is done by this function. So we will sort by probability and we select the one with the highest value. In this way, we reduce the number of paths, and also for this purpose, we want to have just one explanation path for item. We don't need more. But this can be useful maybe to generate explanations which are more complex. Aggregating more paths can be an interesting thing to do. Okay, and here you can see how we have done that. So as next step, what we need to do is to create the top K. So for create the top K, what we're going to do is to use the best predicted path, sort them by score. So the user product relevant score, which is in the position 0. And then if they have the same score for probability, and take the first N, which in our case is 10. This will create the top Ks for every user. If we take a random user, for example, and we take the first element, you can see that this is the recommended product, this is the associated path, which ends with that product. Okay, then for the evaluation, we will measure the NDCG, recall, and precision. So the NDCG, I think most of you are familiar with it, but it's a metric that measures the quality of a ranking. So you consider the position with a weighting factor. The recall that measures the number of correctly recommended items among all the possible recommendations for the user, so Dataset in our case, and the precision that measures the number of correctly recommended items among all the recommended items. So in order to evaluate, what we do is to go through all the top case and store in the hits based on the index, which means the position in the ranking. If we have done an hit, so with 1, or if not, with a 0. So an hit is obtained when the product which is recommended is in the test set of the user. As you can see here at the end, we are saving all the NDCG and the precision record for every user in this dictionary, and we will use that to calculate the mean. So the result that you see here are the mean of the whole data set, 0.29 NDCG, and these are the values for the precision and for record. So now that we have evaluated the model, what we want to do is to generate the final explanations. So, and to do that, what we are going to do is to use the template function that we defined before. So the template function will take the path and transform them based on this length to a textual explanation. As you can see here, the paths that we saw before have been transformed to a path which is more understandable, where the entities are converted to the real entities. For example, Boys Don't Cry is recommended to you because you watched Elizabeth, also watched by this number, because of course the users, we cannot put them with an entity. Okay, and this is for PGPR. For Café, it's pretty much the same thing, because we have standardized the saving of the paths, so they are saved in the same format. So we're going to do pretty much the same steps. And I just wanted to show how they are different. For example, here you can see that Café has the reverse relation encoded. So we have watched and also reverse watched, for example, composed by and reverse composed by. And these are some details. And but what we are going to do is pretty much the same thing. So group the explanations by user and product, and perform the evaluation. And as you can see, Café performs a slightly worse compared to PGPR, but its execution time it's lower compared to PGPR. Finally, we can create the textual explanations, and you can see what they looks like. Of course, as you can see, there might be entities which are difficult to understand, so filter preprocessing could be useful here to clean better the explanation for the final user. And finally, we will see some insights about the last developments that we have done about the explanation quality. As we saw before with Mirko, we defined metrics that measure properties of the link interaction, the shared identity, and the path type. And something that we have shown with the last work is that there might exist more properties related to the paths that are not being considered yet. For example, when we measured the diversity of the link interaction and the diversity of the shared identity, we saw that our models created decrements in those values. So there may exist a lot of different metrics that we don't know yet, and are influenced by how we generate explanations. And to conclude, something that I wanted to show is a use study of our latest work when we introduced this metric in the entering process. And you can see that this is the standard PGPR. So when we measure the recency, we have 0.5 as a value on average. And this is when PGPR means that we have optimized for recency. So all the linking interactions are based on very recent interactions of the user. And this is recency in the processing, and this is the recency in post-processing. And the problem that we saw is that when we use the post-processing, for example, a lot of shared linking interaction are getting repeated. As you can see, Jurassic Park has been repeated 4 times, Batman 2 times, Roman System 2 times. So this side effect is something that exists, but we could not measure that without metrics. And using these metrics during the train, we can see that mitigates this side effect. Here you can see how the linking interaction are less repeated compared to the post-processing only. The same thing, we discovered the same thing also for popularity and diversity. The diversity is very interesting because the original model produced all the explanations which are based on washed, so they are not very useful for the final user because are based on another user which cannot be trusted, let's say. While our model produced on average 0.5 of diversity, so we have top K which is composed by more different relations. So that's it for this part. I hope you enjoyed, and regarding these notebooks, these notebooks should work. So I will invite you to try them locally on your machine, or downloading them or uploading back to Collaboratory. But in any case, I will keep the repository and the directory updated. So if you don't want to miss anything, just follow our sources. So questions? Yes.
Thank you so much. This presentation was awesome.
Thank you.
Could you please show me what's in those like text? Show like the full text of like we recommend you do better. So this text.
Yes.
Somewhere. It's like
Yes. Sorry. So to repeat the question for who is watching from home, how do we obtain this textual explanation? So here it was the original path, right? Which is the one produced by the model. Then we use a template which is pretty much a function that takes the path and produces the textual explanation. And the template is defined here. Yeah. Exactly. Yes, exactly. Yes, if you're talking about the name, you can see that we load that using the entity to plain text.
So do I understand correctly that the CAPTCHA and GDPR are two different methods to accomplish the same goal, or are they
yes.
Yes,
they have. Inside this model, there is an internet to juggle the method, because the methods inside are mapped in different ways. So maybe you need to do different operations to extract the knowledge. This is a common problem, I think, with reasoning path models, is that they are not unifying at all. Doesn't exist a library that contains all of them. They are all different in the file system, etc. So you need to perform a lot of mappings and also a lot of manual definitions, for example, for the meta paths. And this is a huge problem also for reproducibility if you think about it. Okay, I hope I answered your question. You're welcome. Okay,
there is another question here.
Wait, Mirko, we have one question here, and then I will answer the question in chat. Yes. Yes.
Or is it because the model is biased towards showing the item
Okay. Yeah, that's a great question. So the question is why we have let's say a lot of explanation which are based on watch. There is something like a bias toward that relation, and I would say yes, because the watch relation is very prominent in the data sets. Because just imagine with movements, you have 1 million interactions, and then you have the knowledge graph, which is composed by 300,000 triplets, which is smaller, and so this bias in the distribution of the paths will propagate also in the explanations. And our metrics, the diversity, in some ways resolve this problem, increasing the diversity, but it depends. And also to answer the first part of your questions, the relation that exists depends by the knowledge graph that you have. Sometimes you don't have enough information to model, and depends by the knowledge graph and the metapaths that you define, which is always a subset of the information that you have in the graph. Okay, so yes, these are the two parts. Did I answer your question? Yes.
You also showed the different attributes of Jurassic Park. So there's these big nodes, popular titles, that then serve as a source to others. So if I want to show stakeholders, you might say, you know, I'm not really convinced that Jurassic Park is the reason why you need it. So I want to approach my, you know, those repeated activities.
Okay. So you are asking about the why we decided to use the popularity, right? Did I understand correctly? Okay. Yeah, we are sorry. We are out of time. Please write me, and I will answer your question. All right. Yes, of course, later. not online later. Okay. Fine.
Yeah.
We are really late on time, so we will go for the open challenges with Mirko, Marras, and
Yes.
yes.
Yeah, Giacomo, there are also two questions in the chat. You can answer them while I'm talking. So sorry for the previous issue with my laptop. Now should be okay. I will share again. Giacomo, you should stop sharing. Okay, great. Thanks. Can you see my screen?
Yes, we can.
Thanks, Ludo. Okay. So let's use a few slides to discuss some prospective research directions based on what we have seen in this tutorial. So one first challenge is related to the EKG component. So running knowledge-based recommender systems in a novel domain naturally assumes that a knowledge graph is available for the considered dataset. However, a wide range of datasets adopted for recommendation research are not accompanied by a supporting knowledge graph, and therefore they are less explored in this class of systems. Furthermore, collecting and cleaning the source data about the other relevant entities for creating a knowledge graph is often hard and time-consuming. Therefore, devising semi-automatic methods for knowledge graph generation and quality checking is a promised research direction from this perspective. Next, currently most KG recommender systems build a graph by incorporating item-side information only, while fewer models consider user-side information. However, user-side information such as the user network or the user demographic information can also be naturally integrated into the framework of current KG-based recommender systems. For instance, recently, Fan et al. Used the GNN to represent a user-user social network and a user-item interaction graph separately, and shown that this model can outperform traditional collaborative filtering-based recommender systems with user social information. And another recent paper from Shah et al. Integrated user relations into the graph and shown the effectiveness of this strategy. Therefore, considering user-side information in a knowledge graph could be another research direction. Knowledge graph embeddings methods have been used in all the three kinds of knowledge-based recommender systems, as we have seen. However, there is no comprehensive work to suggest under which circumstances, including the data sources, the recommendation scenarios, and the model architectures, should a knowledge graph embedding method be adopted. Therefore, comparing the advantages and disadvantages of knowledge graph embedding methods across conditions is still an open research question. Explanation quality is a broad topic, as you can imagine, so its full assessment would be impossible in the scope of a single research study as the ones appeared so far. Furthermore, testing explanations with user studies and online is expensive in terms of costs and time. An offline evaluation matrix for explanation quality can help to narrow down the set of recommender systems alternatives to test with real users. However, the proposed offline properties and matrix are not exhaustive by any means, and further studies should be conducted. Traditional beyond accuracy metrics that have been explored in the traditional recommender system research, like serendipity, diversity, and novelty, can be further elaborated in the context of reasoning paths, as we have seen with Giacomo before. We therefore envision that conducting further studies to derive offline metrics more coherent with real-world scenarios will be an interesting direction. Recently, works on cross-domain recommendation have appeared, and the motivation is that behind them is that interaction data is unbalanced across domains. For example, on the Amazon platform, the book subset is larger than other domains. With the transfer learning technique, interaction data from the source domain with relatively rich data can be shared for better recommendation in the target domains. And in this sense, Zhao et al., for instance, introduced the PPGN, which puts users and products from different domains in one graph and leverages the user item interaction graph for cross-domain recommendation. Although this model outperformed the other state-of-the-art methods significantly, the user item graph contains only interaction relations and does not consider other relationships among users and items. Therefore, it could be promising to incorporate different types of user and item side information in the graph to improve the performance of cross-domain recommendation. And as we highlighted in the explanation evaluation part, there is plenty of work starting to propose online and offline metrics for explanation quality evaluation. As these metrics have appeared, recent studies like the one we performed for CGIAR and for the extension in the journal that you have the references for them in the slides, have also shown statistically significant differences and therefore unfairness, also related to the quality of the explanations provided to the users. These findings call for a deeper assessment of the impact of knowledge-based recommender systems and their explanations across demographic groups, and also call for countermeasures against the disparities. Another interesting research direction, therefore, considers the biasing methods tackling fairness of explanation quality, going beyond the fairness related only to the recommendation utility. Again, knowledge-based recommender systems, such as those based on path embeddings, leverage the entities in a path along the KG to generate the explanation for a given item, as Giacomo shown. In the movie domain, for instance, possible entities include the movies, the actors, the directors, and so on. However, being explanations, let's say, another way for someone like an actor or a director to get visibility, it should be considered the extent to which certain entities end up appearing more often than others in explanations. For instance, it can happen that a very popular actor is often mentioned in an explanation, emphasizing even more biases and filter bubbles, currently studied mostly on the items being recommended, but not in the explanations. So we believe that controlling the fair exposure of entities pertaining to humans in the explanations will be an important objective of future works. Okay, before closing, we would like to ask you to take 2 minutes to provide us with feedback for improving future versions of this tutorial, and that's it. Maybe you can scan the QR code or save the URL, and you can take a few minutes after the tutorial to help us improving this tutorial. Giacomo, Ludovico, I think that we are going to close. If you want to say something, otherwise I can close.
Okay, no, we're here. So thank you very much for those who attended this tutorial, and we hope you enjoyed it. As we have mentioned in the website, the slides, there's also some questions online. The slides will be shared after the tutorial, probably not today, because in Italy it's quite late now, so probably it will be tomorrow. And the notebooks are online and we're available via email for anything that you might need. Again, thanks a lot for joining us and for your time. We see you around in the conference. Cheers.
Ludo,
Mhm.
I will save the chat because there are a lot of interesting questions, such that you can answer later, maybe at the conference.